Hi, my name is Jacob Mirth, and this is my video lab report for Physics 2211 at Georgia Tech. In this lab, I examined a rolling cart on a track with negligible air resistance and friction to determine its constant velocity. First, I will introduce the experiment, including the key concepts I used, the system and surroundings of the experiment, and the initial conditions placed on the system. Then, I will explain how I analyzed the observed motion of the cart using the tracker software. After that, I will go into depth about how I coded a computational model of the cart's motion using fundamental physics principles to construct a predictive model of the cart's motion. Then, I will show how my predicted motion compares to the observed motion of the cart. Finally, I will answer some fundamental questions about the experiment and explain what I learned. This lab investigates the motion of a rolling cart with constant velocity. According to Newton's first law, in order for an object to have constant velocity, the net force on the object must be equal to zero. In this lab, we assume that air resistance and friction do not act on the cart, so the net force on the cart is zero. The formulas I use for the lab are derived from Newton's second law to give a velocity update formula and a position update formula, based on the initial conditions, net force, average velocity, and delta t. For this lab, I applied an initial force on the cart before data collection was started to get it moving at a constant velocity. As seen in the diagram, after the initial applied force, the only forces on the cart are the normal force and the force due to gravity, which perfectly cancel each other out, leaving us with a net force of zero. This results in a constant velocity motion. I analyzed this video clip of a low friction rolling cart on a track in the tracker software to obtain data for the position of the cart at each time interval. I chose the left direction as negative, which resulted in a downward sloping graph of position versus time as seen in the right side of the video. This acted as my observed data set. To construct the computational model of the cart's predicted motion, I used the provided starter code and implemented Newton's second law into the while loop to indicate the position of the cart based on its constant velocity at each time step. I calculated the initial velocity from the observed data as seen in the right side by measuring how far the cart moved in the video clip, divided by the time it took. Since the velocity was constant, the initial velocity was equal to the calculated average velocity. The excerpt from my code in the bottom left shows how I implemented these equations into the Python script for the initial conditions. I did not change the mass of the cart because the mass cancels out anyways in Newton's second law when the velocity is constant. I set the initial position to 0, 0, 0 to simplify the data analysis later on. The cart traveled to the left, so I also set my initial velocity to a negative value. Here you can see how I implemented the previously mentioned equations and initial conditions into a while loop in the Python script. This generates a data set which shows the cart's position at each time step, updating its position after each iteration, based on the position update formula and the initial conditions I previously explained. Here are the two graphs representing the data from both the observed dataset from Tracker and the predicted dataset from my computational model. As you can see, the predicted dataset matches the observed data fairly well. However, towards the end of the graph, the observed data starts to flatten out, while the predicted data continues in a perfectly straight line. This indicates that the actual motion of the cart is not in perfectly constant velocity. Speed and velocity of the cart start to decrease, which means that there must be a small force in the opposite direction of its motion. This is likely due to the frictional force and air resistance acting on the cart, since these forces were not accounted for in the computational model. Let's look at some essential questions. I chose the left direction to be negative for my position, which resulted in a graph with a negative slope. What if I flip the axes? This would simply flip my graphs so the slope was positive. It would not change the core story that my data shows, which is the net force on the cart was not zero because of a small frictional force that was not accounted for in the computational model, thus resulting in a decreasing speed and velocity. This being said, the zero net force assumed in the computational model was not justified. The data clearly shows that there's a small force acting on the cart in the opposite direction of its motion. With the current setup of the lab, it is very difficult to know the exact combination of pushes and pulls acting on the cart to determine an accurate net force. One way to increase the accuracy of this lab in the future would be to decrease friction and air resistance by using surfaces with very low coefficients of friction. Additionally, the force of friction could be implemented into the computational model itself, but this would require some data collection on the efficiency of the cart used in the experiment. Thank you for watching.